questions, I have a few, not announcements, but like putting things in perspective for us all. Inshallah, we already finished everything that has to do with the street flights, level flight. So we will, inshallah, today and Monday, we will be finishing the topic of steady flight, that's chapter 5, all of chapter 5. By Wednesday, we'll be having chapter 6, which is a very short chapter, and we'll pick and choose certain parts of it to finish the performance. And the design will start in chapter 7 and 8. That would be week 9. So next week, inshallah, we will start officially forming you into groups for the design project. And as we go through weeks 10, 11, 12, we will have the design of a propeller driven aircraft. And that will be your design project as we go. So as we learn chapter 7, you will be doing these tasks with the design. Then in the last 3 weeks, 12, 13, 14, we are going to have the design of jet aircraft. It's a part of the course, but your project will still go on, will be going on for more than 3 weeks. You will do the project maybe 6 weeks. Okay, but the jet aircraft part will be there for the course as well. So I need you to think of your teammates. If you have suggestions, keep them in mind, start making lists. We need a team, typical ideal team would be between 5 and 7 students. Okay, with almost 40 students here, so we have like 8 teams, 7 teams maybe. Okay. Start preparing like a list so that once we release things officially, you are ready with your team. I always like to give you guys the chance of selecting your teammates, managing your team, and we're going to talk a little bit about team work management, leadership, the ethics issue, work distribution, and so on. But we will do this in proper time right after we finish chapter 6, inshallah. Okay. So this was just a heads up of what's going on. I also got a question of why are you studying all the aerodynamics, propulsion, where are things heading? So maybe it's about time to just take a break and see where are we and where are we going. Chapter 2, we looked at the aerodynamics. So we had some important relationships related to L over D max, V max now. At that time, they were like pieces of a puzzle. We didn't know what we were going to do with them. Okay, so today we are going to use this. Chapter 3, we looked at the engines, different types of engine, maximum thrust variation means density. Again, we didn't know how to do this. What are we going to do with them? Chapter 4 was simply equations. Chapter 5 is performance, and performance is the link between the science, the equations, the L over D, and everything with the design. Because in design, there is a set of requirements at the beginning. You don't say, if you are a client, you don't go to engineers and say, okay, make me an aircraft that has L over D equal 20. You don't say that. You say, make me an aircraft that will take off in no more than 3,000 feet, or that it will climb to an altitude of 30,000 feet within 1 minute, 2 minutes, whatever. Okay, so the link between the science, the equations, and the design is the performance. And that's why we have 2 performance chapters in the textbook, chapter 5 and chapter 6. Chapter 5 is for steady flight, and by steady flight, we mean flight with no accelerations. Whether that flight is level, this is what we had in the past few sessions, or that flight is not level, the aircraft is either climbing or going downward, descending. This is what we're going to have today. Okay, so chapter 5 was steady flight. The key word here is that we have no accelerations in chapter 5. The aircraft speed does not go up or down, it's just constant. In chapter 6, we are going to look at situations where we have accelerations. So the aircraft is turning, so we have centripetal acceleration. The aircraft is landing or taking off, so it's accelerating or decelerating, and so on. Okay, so this is the big picture. And that's why the textbook was arranged to 3 parts: the basics, chapter 2, 3, 1, 2, 3, 4. So 1, 2, 3, the performance, 4, 5, 6, and the design 7 and 8. Okay, so I'm right now in the middle of the performance part, the link between the equations and the design. Okay, so I hope this puts things into perspective. So what we'll be doing today, we are going to continue the steady flight. That means no accelerations, but we are going to look at non-level. We are going to look at situations of climb and glide. And we're going to see that this translates to design requirements. Okay, design requirements sometimes on rate of climb. So an aircraft is required to have a certain, to be able to climb within several thousand feet per minute, for example, and maximum climb, and the velocity of maximum climb angle. Okay, so these could be requirements for certain aircrafts. We are going to look at the glide, and we are going to also look at what we mean by the ceiling, both service and absolute ceilings. So this is what we will be doing today, inshallah. Okay. What remains in chapter 5, which is the steady flight, are just 2 topics: the range and the endurance. The range, how far you want the aircraft to fly, so what's the distance in miles, and the endurance, how long you want the aircraft to fly in hours, 3 hours, 4 hours, 10 hours. And there are two different performance parameters. And we are going to have these 2, inshallah, on Monday. Wednesday will be chapter 6, turning, landing, and taking off. And then right away on week 9, we will start the design chapter 7. Okay. So let's start our non-level and steady flight. That means the aircraft is climbing at a constant speed, and it's making an angle theta with the horizontal. And in many cases, students would confuse this angle theta with the angle of attack. Okay. Let's say the wing on this aircraft is attached in here, and the chord line is along that axis. What is the angle of attack of this aircraft?
0.
0. Okay, it's very important to realize that you have, as I always tell your colleagues, you have like graduating engineers who would do this very simple mistake. An angle of attack of this aircraft is 0 if the chord line is along this line, because the angle of attack is the angle between the chord line and the free stream. And the free stream is determined by the direction of motion of the aircraft. If theta is the angle of attack, that means this aircraft is moving to the right. Okay, so it would be an angle of attack of 20 degrees, 30 degrees. Very few aircraft would fly at these angles. In fact, some superior aerodynamic aircraft can fly at very high angle of attack. MiG-29, Sukhoi 27s can have a 90-degree angle of attack for a few seconds. Okay, so the aircraft could be totally vertical but moving to the sides, or even could be like a little bit inverted. Angle of attack would be 120 degrees for this aircraft, and you can YouTube them and see them doing like these miraculous things. So this aircraft is flying up, climbing at an angle of climb theta, and at a constant speed. That's what it means to be steady flight. The whole chapter 5 is steady flight. So with this aircraft is under equilibrium. It's not called equation of motion because we don't have acceleration. It's equation of equilibrium. Forces along this direction all balance to 0. So the thrust minus the drag minus the component of the weight is 0. Forces along this direction balance to 0. So it's the lift minus the component of the weight is 0. Now, if I want to start analysis of the climb, I need to determine what's the climb rate. The climb rate is the vertical speed. Okay, so the vertical speed is V infinity times sine the angle theta. So it's V sine theta from here. But I can get sine theta from the first equilibrium equation to be T minus D over W. So it's T minus D over W, and that would be the sine theta. If I multiply by V infinity, that would be the rate of climb. Okay, so the rate of climb is TV minus dV over W. But someone can look at this term. So someone can see T minus D over W to be sine theta, and then multiply it by V. That will give me the vertical component. Someone else might read it differently. He might read T times V is power generated by the engine. D times V is the power used by the air as friction. So TV minus dV is nothing more than the excess power, the extra power generated by the engine than the power needed to overcome the drag. The aircraft will climb if we have this excess power in here divided by W. So I can say the rate of climb is simply the excess power over W. Okay, so two different ways to look at the rate of climb, V sine theta or excess power over W. Both are exactly the same. Okay, so that's the rate of climb. The vertical speed rate of climb is V infinity sine theta. Now, some designs require a certain rate of climb. For example, let's say you have an interceptor aircraft. It must have a rate of climb for no less than 10,000 feet per minute. That means every minute it has to climb up more than 10,000 feet. Okay, but sometimes, so that's the rate of climb. So that's the vertical speed that we have in here. This is what matters for the aircraft. But in some cases, the condition is not on the rate of climb, it is on the angle of climb. We need to make the climb as steep as possible. That means once the aircraft takes off, it needs to have a very high angle. Now, what are the situations where we need to do this? Well, there are a couple of them. One, if there are, let's say, obstacles nearby. The airport is within an area surrounded by buildings or mountains. Well, buildings should not be there in the first place, but let's say mountains. So you want you don't want the aircraft to climb at a high rate. No, you want to climb at a high angle. So you need to maximize the angle of climb. Another situation would be an aircraft taking off from metropolitan areas where you have so many people living around. And noise is an issue, and noise will be a constraint on our design when we do. So you want to lower the noise level by making the aircraft climb at a very high rate and then turning. Okay, so that's another situation where angle of climb is important. Since we looked at the rate of climb here, let's look at the angle of climb. And derivations that we're going to see today, not so many actually, maybe 2 or 3, are all based on the equilibrium equations. We don't have any new equations other than these. We'll just substitute from one to the other and our previous knowledge of aerodynamics and thrust. So we'll start putting pieces of the puzzle here. Okay, but of course in design we'll use the final equation. We will not derive them every time. So if I want the angle of climb, the theta, making theta here is the unknown that we have, all I have to do is to look into these two equations and try to get theta out of them, solve for theta. Okay, so what we will do is from the first equation, we know the rate of climb TV minus dV over W. Okay, that means sine theta is T minus D over W. But for the second equation, I can take the W out in here and replace it by L over cosine theta, so that I will have cosine theta and sine theta in here. But since climb angle is typically not very large, let's say how high a climb angle could be, 6, 7, 10 degrees, maybe. So although it seems so high, but it's not really. Don't judge an aircraft by looking from the back of the aircraft when it takes off, because you will have like an illusion of the angle being very high. You need to look at the aircraft path from the side to see that the angle is not really that high. This is very clear with all the Tornadoes and F-15s taking off from the base nearby. If you see the aircraft from the side, you'll see the climb angle is not really that high. Okay, neither the descent angle, of course. So if the angle is small, I can assume that the cosine is very close to 1. And if because it will be 0.9 something. So if it is 1 in here, then sine theta is T over W minus 1 L over D. Now, why are we doing this? Because now we can get the angle of climb related to some important known aerodynamic criteria, which is the lift to drag ratio. And you have been examined in this a couple of days ago. And you know that L over D can be maximum, and there is an expression for that. Can you remember what's L over D max? It was the simplest of all the equations in the formula sheet. L over D max equals?
Is it the square root of 4 CD initial K?
Yeah, 4 CD not K. It only depended on the drag polar. So this to be 1 over root square 4 CD naught. I will put it here. That will give me sine theta max in this case. Up to here, it was sine theta, but if I use L over D max, it will give me sine theta max. Not minimum, maximum, because I have a negative sign in here. So sine theta max, I need to put L over D max, which is root square 4 CD naught. And this would give me the maximum angle of climb. All I have to do now is to say, okay, I need also to continue, get the thrust out of the equation. Let me use the aerodynamic characteristics. Well, L is equal to the weight cosine theta. That's the second equilibrium equation. The lift is 1/2 rho V square S. And since CL is root square CD naught, let's get rid of CL in here and substitute back into the equation. We can make the only unknown in the equation V theta. So this equation, or that equation, tells me the angle. And if I keep V theta on one side and move everything to the other, will get me the speed at this angle. Well, does that mean that you cannot climb at the maximum angle of climb with any speed? Yes, you cannot climb at the maximum angle of climb at any speed. It has to be a certain speed that will keep the two equations of equilibrium satisfied. In order for these to be satisfied, although you do not see speed here, there is one speed for each angle. Where is speed in this equation? Where is speed hidden in this equation?
The second equation.
Yeah, in the lift, it's in here. And the lift is related to the angle. The angle here is related to the drag and the thrust. So only one speed per angle. So if you want the maximum angle, you have one speed. Okay, so that's the speed at which jet aircrafts can climb with the maximum angle. And if this is the speed and this is the angle, then the rate of climb in that case will be the speed multiplied by sine the angle. So here is the rate of climb, the speed multiplied by sine the angle. Please bear in mind this is the rate of climb at the maximum angle, because I have different rates of climb. Whenever I change V here and theta, I will get a different rate of climb. When theta changes, V will change. Theta change, V change. Theta and V pair, theta and V, I have a certain rate of climb. But if I choose maximum theta, there is one speed that goes with it, and there is one rate of climb that goes with it, and that's the rate of climb. Okay. So this rate of climb is for the maximum angle. So I have a rate, here is the maximum rate of climb, and this is the rate of climb at the maximum angle. Of course, the rate of climb here will be less than here. The angle is more, but you will climb slower. And that makes sense. It's just like you going up a hill. If you have a very steep hill, you can climb slower than if you have a shallow hill. And both of them will be, of course, slower than if you go straight and level. Okay. Any questions up to the velocity of a climb, maximum climb angle? Okay. Now in these two slides, you will see thrust everywhere, T, T, T in the equation. So that was valid for jet aircraft. Propeller aircraft will deal with power, but we don't have much of a power equilibrium equations. Equilibrium equations are in terms of thrust. This is one thing. The other thing is that here we did not discuss the variation of thrust with speed, because for jet aircraft, thrust is almost constant with speed. It changes with altitude, but not with speed, or not quite with speed. So it was easy to deal with it as constant. However, once we start looking at propeller aircraft, thrust is not going to be constant because it's inversely proportional to speed. Eta P over speed. Now, if you keep this T variable in the equation, this will complicate things considerably. Imagine this T has something over V. If we put it here, something over V, and then we have here V square, and you try to solve for V, it will be an equation of the degree 4. It's going to be a mess. Analytically, it's going to be, and we will end up doing like a lot of math, and at the end we will get a fourth order degree equation that we will not be able to solve. So solution is done approximately for propeller aircraft. Okay, and the details are beyond the scope of both the book and this course. So we'll just use them knowing that these are approximate solutions to the same equations if we have a propeller aircraft, because of T will be variable with V. But it's again function of the same parameter. The wing loading, W over S, we see it here and here. The angle of maximum steep, the maximum climb. Okay, so we get it. This is the speed at the angle. It's a function of K CD naught. We can see here K, we don't see CD naughts. It's a function of the density and it's a function of density. So they are close. They are close. Okay, and the angle is calculated from a rather more complicated equation. You see the angle here was simple. T over W minus 1 L over D. But since T is variable, the angle here is more complicated. Okay. So for propeller aircraft, the results are approximate. They are not exact. This is one thing. The other thing is that, remember when I was saying in the figure, the steeper you go, the slower the aircraft will be. That means if the aircraft flies straight and level, it has a certain speed. If it flies at a maximum rate of climb, it has to be at another speed, which is slower than this, and this one, a third speed, which is even slower. Now, there is no guarantee that this last speed, or even this one, this one or that one, could be lower than the stall speed. If the aircraft wants to clear an obstacle like this, the speed that we calculate from here, maybe it happens to be less than the stall speed. Let me give you an example. An aircraft has a stall speed of 100 nautical miles, 100 knots. And we calculate the speed required for it to fly at an angle of 20 degrees. And we found that speed to be 80 nautical miles. So aircraft stalls are 100, and we calculate the maximum angle turns out to be 20. And the speed at this 20 is 80. Physically, what does that mean? What does that mean?
I think the aircraft will stall.
Yeah, the aircraft will stall before you slow it down to 80. That means you cannot climb at this maximum angle. And the maximum angle will be determined by the stall speed, not by the calculations that we have done. Okay, so there is a caution in here in the calculations. Once we calculate this v theta for the propeller or this v theta max for the jet, we need to check that it is above the stall speed, because if it's below the stall speed, this is an incorrect result. This result comes only from equilibrium of forces. It doesn't include the effect of aerodynamic stalling. Okay, so that means the aircraft will not achieve the 20 degrees maximum angle. Maybe it will fly at 18 degrees maximum angle of climb. Again, maximum angle of climb, not maximum angle of attack. That's totally different. When I say stall, that means the aircraft will stall. When I say it will stall here, for example, this aircraft will stall at this maximum angle, not because the angle of attack is this 20 degrees. No, because the stall angle at zero angle of attack, the stall speed at zero angle of attack is that speed it's flying. It's because of its low speed, not because of the high angle. Is this clear?
Repeat the point again.
Repeat again. We say in order to achieve maximum angle, the aircraft has to slow down, right? Vmax is less than V straightened level. We found that it might be slower than the stall speed. Assume the aircraft is going like this. It's going like this, and the air is coming like this. And I'm telling you, it will stall. Now that stall is not because the angle of attack is very high, because that's not the angle of attack. The angle of attack is actually zero. Speed is coming like this, the aircraft is flying up, the chord is along the speed, the angle of attack is zero. It will stall because the speed is low. For every angle of attack, there is a stall speed. Does that make sense?
Yes.
Okay, so an aircraft flying straight and level. Let's say the aircraft is flying straight and level. Okay, so straight and level has a certain angle of attack and a certain stall speed. If it's climbing, the speed could be lower than the stall speed. Of course, physically that cannot happen, so it will not climb at this angle. It will climb at a lower angle. So that's the caution that we have in here to bear in mind. Okay, any questions? Now we have a final issue related to climb that we are going to tackle before we look at our example. Now we're going to look exactly at the opposite of climb. Rather than the aircraft going up, the aircraft will be going down, but not with powered flight, but with all engines failing. So that means the aircraft is gliding downwards without a sound, no engines are running. They all failed and the aircraft is going down. So the question will be, what would be the angle of descent? It's not going to be the angle of climb, the angle of descent. And what would be the range of the aircraft before it hits the ground? How far it can go? And if you have been a movie fan, you probably have seen the Sully movie by Tom Hanks, which main theme was basically this issue. The angle of descent and whether the range of the aircraft was enough for the aircraft to land on an alternate airport that was nearby, or he made the right decision by ditching the aircraft into the river. Okay. So the gliding condition is a constraint and requirement on aircraft, all aircrafts, mainly transport aircraft, of course. If the aircraft loses power, it should be able to fly for a certain distance. And to maximize that distance, we have to minimize the descent angle. Of course, we wish the aircraft can fly straight at level, but we know that will never happen. It has to go down, but let's keep it down as shallow as possible. Let's keep this angle as small as possible. So in order to find the calcs for this, we will also use the equilibrium equation. These are exactly the same equation that we had before when we were talking climb, except that there is no thrust in this case. T is 0, so we will end up with two simple equations. Okay, so here are the same two equations. Since we got thrust out of the picture, I can divide and I can get tan the angle, and that will be L over D because W will cancel. And it is as simple as this. The angle of descent of any aircraft is simply tan the angle is the inverse of L over D max. And L over D is a function only of the drag polar, CD naught and K. So tan theta is root square for CD naught K. That's why the drag polar is so important. It determines how shallow the aircraft will glide down to Earth if engines fail. Okay, and if I have this angle, I can get the speed right away from the speed equations that we had before. Substituting with the angle, I will get the speed to be root square 2 cosine rho CL, same expression that we had before, but now with a new angle. Now, this is the speed if you want to fly with that angle. So the pilot has, because the pilot does not adjust the angle, it's not up to him. This angle is determined simply by gravity and aerodynamics. The pilot can adjust the speed. If he gets that speed, he will fly with that angle. And that will give him the longer distance he wants to get to an alternate airport. How can a pilot adjust speed if he has no engines?
By using the flaps.
Using flaps, what does that do to speed? Does it increase it or decrease
Reduce
it?
the speed.
Reduce.
The speed.
So he can decrease speed only by the flaps. So flaps can slow down. It's just like brakes, right? But what if he wants to increase speed? How would he do it? Because the question was how he changes speed, not how he decreases speed.
Using the weight, doctor, I think.
Use the angle.
What do you mean by the weight? We can throw someone out of the window if you want, but that's not going to be a solution. How can he change the speed of an aircraft without the engines?
By maximize the angle.
You are the pilot in the cockpit. Where is the control that changed the angle? We don't change the angle. The angle is determined by mechanics, by the equations. The angle is the result. It's not the input. The question is, what is the input that will change that angle?
The elevator and the airline?
Yes, the elevator, not the ailerons. The ailerons turn right and left. It's the elevator. If the pilot pulls on the stick to increase the elevator angle, that will mean the aircraft's angle of attack will increase and the speed will slow down. So that's how he slows down. If he pushes on the stick in front of him, the elevator will go down, angle of attack decrease, and the speed will increase. Okay, so the controls are through the elevators. He adjusts the speed, and if he gets this particular speed, then he will get that optimum angle. Of course, in a cockpit, he will not go and do his math and use a calculator to do that, but it's set by the regulations. If you are at a certain altitude, you lose the engines, fly at this speed, adjust the speed, so he will use the stick to adjust the speed, and then the aircraft will be flying at the minimum angle of glide. Okay. Any questions up to this point? Okay. So we are going to see an example now. Consider the Gulfstream 4, which is, I think, an aircraft you know by heart now, everything about it, in all the examples of Chapter 5. This business jet is flying at 30,000 feet. Then a total loss of engine thrust. Calculate the maximum glide path angle. So I need the angle with the maximum glide path. Minimum glide path angle. That gives me maximum range, of course. So I need the minimum glide path angle, theta minimum, and the maximum range covered with this theta, and the corresponding equilibrium glide velocity of 30,000 feet and at sea level. Why is that? Why he's asking about two things, 30,000 feet and at sea level? He's asking about the speed at two different altitudes. Now, if I go back, you will see this speed is a function of what? Density. So if you want to get that angle, and you are at 30,000 feet, you use the density of 30,000 feet. If the pilot goes down to 20,000 feet, he has to change the speed to keep going with the same angle. So as he descends, that speed has to change every now and then to maintain that distance, because it's a function of altitude. That's why in the problem he's asking you calculate it at two altitudes, 30,000 and at sea level. Okay. So let's see. I need the minimum glide path angle. That means I need theta. Theta is 1 over LD max, so I need L over D max of this aircraft. Of course, we had the drag polar of this aircraft so many times, so we know that root 4 CD naught K of this aircraft we calculated before. L over D max in a previous example 5.4, I guess. This one was root square 4 CD naught K, and it was 14. Okay. So I have this 1 over 14 turns out to be 0.06. Inverse 10 gives me about 4 degrees, 3.96 degrees, about 4 degrees. So this aircraft, if it loses the engines, will descend with an angle of 4 degrees. Now, if I know that the angle is 4 degrees and the aircraft is at 30,000 feet, what would be the range until it hits the ground? Well, the range in this case will be h divided by tan the angle, right? Because this is the range and this is the height. So the range is the height divided by tan the angle. So h over tan the angle, 30,000 over tan, 4 degrees, giving me 432, about 433,000 feet, which is 82 miles. The aircraft has to, or at most, at best, if he adjusts the speed, he can fly for 82 miles. There is nothing the pilot can do that will make this number 83 miles. Nothing. Okay. Because the aircraft has certain L over D, it's already designed, nothing can change that. However, a designer, since the aircraft is still being designed, can do changes to make this number, if he wants, if it's required, to be 100 nautical miles, 120 nautical miles. What can he do? Well, he can do a lot for L over D max. Okay, so glide distance, this range here is always a requirement in transport aircraft. GACA has a requirement, the FAA has a requirement, and it mentions whenever you have a transport aircraft weighing more than 50,000 pounds, it has to be able to fly for, let's say, 100 miles descending from an altitude of 35,000 feet. Okay, so that's why it's important for design. Gliding is important.
Doctor.
So, any question?
Doctor.
Yes.
Is there any possibility that the weather conditions would help to increase the range?
Considerably, no. Why do you think? What's in the weather conditions can change this? Remember, you are talking about heavier than air objects. If it was a balloon, well, that's an issue. Yes, if you have a current moving forward, that's fine. But what can you do about this? The only possibility that you have is you can have a headwind. Okay, and that will have like a minor effect because that speed is extremely minor compared to the speed of the aircraft. When you have an aircraft flying at 600 feet per second, how fast the wind can be. Okay.
Yeah.
So a headwind can help, but for what? And you cannot plan on this, and it's variable, and you have to fly ahead of the wing. What if the airport is behind you in the opposite direction of the wind? You cannot design on wind.
Yeah.
Okay.
Yes.
Okay.
I guess.
So, okay. So we have seen the angle, we have seen the range, and the last part would be the speed. What's the speed to achieve this angle and this range? So we need to look into the equation. This is a jet aircraft, so I need to use the equation of the jet aircraft. That's the one that we derived, not the approximate of the propeller, but the one for the jet. So the speed, in this case, here is the formula of the speed. WS, we have it, KC did not have it for this aircraft from the drag polar, and he's asking about 30,000 feet. So putting density at 30,000 feet gives me a speed of 631.2. So the pilot can get the 82 miles if, when he flies at 30,000 feet and loses power, makes the speed 631.2. As he goes down in altitude, the density will increase and that speed has to go down. So at 20,000 feet, he needs to change the speed, slow it down until at sea level. If you put the density here to be the density at sea level, the speed will be 386.4. That what will give him the 82. If for whatever reason, at 30,000 feet, he flies not at 631, but at 700. Well, he can fly at 700, and that's not a good thing. He will go steeper. So he will have an angle more than 5 degrees, and he will end up not getting the 82, maybe getting 75. Okay, so in order to get the 82 and the 4 degrees, you have to keep going with the speeds calculated from this equation at each altitude. So they have to change a little bit every now and then. Okay, so he has to adjust the elevator setting as he goes down. Okay, any question in this problem? Okay. The last topic that has to do with climbing and gliding and changing heights is the ceiling. Ceiling is the maximum height the aircraft can reach. And engineers have a way to define the ceiling. We say when the aircraft is on the ground, that means altitude is 0, it has certain rate of climb. It can climb at a rate of climb of 5,000 feet per minute, 3,000 feet per minute, any altitude, any rate of climb the pilot has. Let's say the maximum is 6,000 feet per minute when the aircraft is at sea level. Then when it's at a certain altitude, the pilot can still climb, but due to the decrease in density, he will not be able to achieve the 6,000. The maximum at this altitude may be 5,000. The maximum he can do here, 4,000. We say we reach the ceiling when the maximum possible rate of climb is 0. That means when the curve of rate of climb or maximum rate of climb hits the vertical axis. Because here, maximum rate of climb is 0. What does it mean? Maximum rate of climb is 0. I cannot climb any further. This is the furthest I can go up. That's the absolute ceiling. Sometimes it is required in the design. It's specified. So you say the absolute ceiling of this aircraft should be 45,000 feet. Okay, so now I have to work with the absolute ceiling. However, in most design requirements, it's not the absolute ceiling that matters, it's the service ceiling. Service ceiling is a little bit below the absolute ceiling, and it's defined as the altitude at which the maximum rate of climb is 100 feet per minute. Why would someone do that? Why do we define it this way? Well, we just a little bit of climb capability for the aircraft that we are not using in our calculations just in case. Think of this 100 feet per minute as the extra fuel that's in your car when your gauge shows you it's empty. We know that your car can go on for maybe what, 10 kilometers, 20 kilometers, 30 kilometers, depending on the car. after you have run dry on the gauge. It tells you it's empty, 0, but it can go on for 10, 20. So we keep this 100 feet per minute, and we design on the service ceiling, and we don't count on them. They are just for emergencies. If the aircraft faces like an obstacle and it has to clear the obstacle, odd situation, for errors in our calculations, for whatever, we keep this 100 feet per minute, and that would be the service ceiling of the aircraft. 100 feet per minute is a very low rate of climb. I always like to relate it to physical things. Our building, building 75, has a height of about 100 feet, about 30 meters, maybe a little bit less than this, if you take it from the bottom all the way up. Okay, a little bit less than this. So that means you need about a minute to clear that building. That's one whole minute of an aircraft climbing just to get above that building. That's a very low rate of climb. But remember, that's the emergency part. Okay. So service ceiling is 100 feet per minute. Ceilings are important in another way because I can use them. I can use the inverse of this rate of climb to calculate the time of climb. Rate of climb is how high you can go per second. If I reverse this, that tells me how much time do you need to reach a certain altitude. And that time sometimes is the constraints that we have on the design. For example, a military aircraft maybe will have a constraint to climb to a 20,000 feet within a minute, okay, or less than a minute. Yeah. So if we invert the rate of climb and integrate it, we are going to have the time of climb. And that's what you have in chapter 5.12. I'll just leave it for you reading because it just, there's no like final equations there. It's just showing you the procedure. You want to calculate the time, invert the rates, and integrate. And with this, we finish the performance during climb, glide, and ceiling. Next time, inshallah, we are going to look at performance in range and endurance, time and distance, and that would be it with chapter 5 with the steady flight. Chapter 6 will be flight with accelerations, and then 7 and 8 will be the design parts. So let's see if we have any final questions here. Okay, I already had taken the attendance, so I think we're okay. Please think of the teams, work 5 to 7 members. If we can form this by the middle of next week, that would be great. I don't want to intervene. I always like to leave it to you. And then we are going to talk about teamwork, assigning tasks, and so on, so that we can do this on the second half of the semester. Okay, Shabab. So if you don't have questions, inshallah, I'll be seeing you on Monday. Thank you.